Assalamu alaikum. We are starting with the chapter of sound today for full syllabus coverage for our GCSE O-level examination. So what is a sound wave and how is it produced? Sound is a form of energy that is transferred from one point to another point without the transfer of the medium in the form of a longitudinal wave, which means that if a disturbance is created in the form of a sound wave, so the medium will not be transferred. The solid through which the sound is passing will not be transferred. What do I mean by a longitudinal wave? I mean those type of waves that travel in the form of compressions and rarefactions, and the direction of travel is parallel to the direction of movement of particles. Over here, you can see we have a tuning fork. When the tuning fork moves inwards, a space is created, and so the particles spread out and a rarefaction forms. Rarefaction has less number of particles in the same unit area as compared to compressions. And when the tuning fork moves outwards, it pushes the particles together, forming a high pressure region called a compression, where the particles are closer together per unit area. So we discussed that sound waves are longitudinal waves that travel in the form of compressions and rarefactions. So if you have a human ear here and a sound source over here, the sound wave will be generated and it will be transferred in the form of compressions and rarefactions. So over here, if I take two consecutive compressions or two consecutive rarefactions, for example, I'm taking two consecutive compressions and their center of compression. This is the center of compression. This is the center of this compression. It's continuous like this. The distance between the two becomes my wavelength that I can denote using the symbol lambda. And we can see that the wave is traveling towards the right and the air molecules are moving to and fro. So the direction of movement of air particles is parallel to the direction of travel of the wave. Now, sound waves are produced through vibrating sources in a medium, a source that vibrates. If I have a tuning fork, you saw it was vibrating. And if I use any loudspeaker or any such sound source, the waves that it will generate would be in the form of a disturbance that will make it a vibrating source. Gases, liquids, and solids have different rates of transmission, different speeds for sound because of the arrangement of particles, and sound does not travel in vacuum. Why? Because we discussed it needs a medium to travel. It travels through vibration of particles, and so it needs particles to transfer the wave. Now, the audible range of frequencies for humans is from 20 hertz to 20 kilohertz. What is 20 hertz and 20 kilohertz? These are different frequencies. This is the audible frequency range for humans. And anything above 20 kilohertz can also be written as 20,000 hertz, becomes ultrasound, and anything below 20 hertz becomes infrasound, but that's not part of our syllabus. In ultrasound, we have several examples. For example, bats use ultrasound to form a picture of their surroundings. If the bats cannot see, they're blind. So you have a wall here and they need to know if there's an object. So here is your ultrasound wave that the bat generates. It echoes, it's reflected back to the bat, and an image can be formed. Similarly, the image of the fetus is formed in that very manner. The ultrasound waves are transmitted to the woman's body and they are reflected by the fetus, and in that manner, your image of the fetus forms. Dogs can also hear ultrasound, but they can also hear us. So that means that their range of hearing is somewhere in our audible frequency range and somewhere in ultrasound, which is why you have special dog whistles that humans cannot hear because their frequency is too high. You also can use ultrasound to clean sensitive artifacts, for example, gold jewelry, that's very valuable. And ultrasound can also be used to measure distances using the same phenomenon of echo. So the bell jar experiment. What is the bell jar experiment? You have this glass jar, a bell jar, in which you have a bell, and there is air inside the jar, air. What happens is, to check if sound can travel in vacuum, you remove the air slowly, and the sound becomes distant and faint. And so here the sound was very loud, but as you remove the air, the sound becomes distant. And when you remove the air completely and you have a state of vacuum, you cannot hear the sound. But once through the pump, air goes in once again, so you can hear the sound once again. Now, the medium and speeds of transmission of sounds. In water, it's 1500 meter per second. And solids, it's 5,000 meter per second. We're taking the example of iron here. And in air, the average is 300 meter per second. So you can see the ratio 1:5 is to 15. 300 times 5 gives me 1500. So here I have it. And 300 times 15 gives me 5,000. So that is the ratio of speed of sound in liquids, gases, and solids. And so we prove the fact that sound travels in a medium using the bell jar experiment. If I want to use a direct method to calculate the speed of sound, we know the formula of speed is distance upon time. Speed is equals to distance upon time. And with that, if you have person A with a pistol, and that's a smoke pistol, so you can also see the smoke as soon as the pistol is fired. And you have person B at a known distance, for example, 16 meters. And the person A fires the pistol, and as soon as person B sees the smoke, they start the stopwatch. And as soon as they hear the pistol, they stop the stopwatch. So for example, that took just 2 seconds. So the speed of sound for us became 16 upon 2, 8 meters per second, which is a very unrealistic value because we know that the speed of sound in air is 330 meters per second. So this was just an example. This is the direct method for the calculation of sound. So what are the errors that can take place in this process? So here again, we have person A with a starting pistol. We have person B with a stopwatch, and we have a known distance of 150 meters. So when the pistol is fired, the person starts the stopwatch, and when the sound is heard of the pistol by person B, they stop the stopwatch. And so what can be the problems here? The problem can be human reaction time, which is 0.5 seconds for humans. That is when they saw the pistol, but they saw the smoke, but obviously they couldn't immediately start the stopwatch, right? And so it took them a delay of 0.5 seconds to start the stopwatch and another delay of 0.5 seconds to stop it. So over here, if you see, for example, it just took them a difference of 1 second. In 1 second, first the smoke was seen, and then after 1 second, the sound was heard. And if there was a human reaction time of 0.5 seconds, both times starting and stopping the stopwatch, that's an additional 1 second that you have on your stopwatch. Or maybe it's subtracted if it took you longer. So that gives you 0 seconds or 1.5 seconds, depending on how you reacted. So that is a huge difference in the original value that was 1 second. And so the ratio of the human reaction time to the time taken by sound is very large. So how can we reduce human reaction time? Taking multiple readings will not affect it here because the reaction time will remain the same every time. What you can do instead is increase the distance. At the moment, there was 150 meters. You can convert it to 1 kilometer, say. The first experiment that took place centuries ago, at that time, there was a distance of 16 kilometers between 2 railway stations, and a cannon was used to calculate this. So if you see the ratio of the time taken by the sound as compared to the human reaction time becomes very little, so we can cancel out the human reaction time this way. Then the effect of wind. For example, there is wind in this direction, and it helps the sound move faster, so the time becomes lesser, and that gives you an inaccurate value. For that, you can first take your readings like this, and then you can switch the values, switch the places of person A and person B. So then the wind will be working in opposite direction that would slow the speed of sound. And so they will cancel out the effect of each other. For echo, you can have an open field. Over here, you see we've taken an open field. Why? Because since there are no objects, so there can be no echo. If there was an object, the sound could have traveled and come to person B in many different ways. One way from here, one way from echoing in another area. And so to prevent that, we just use an open field. Then the indirect method for the calculation of sound, that is through echo. What is echo? Echo is the reflection of sound due to repetition of sound, or the repetition of sound due to reflection of sound. So what happens? You use a clapper to produce a sound wave that hits the wall, and it bounces back, and it's detected over here. And through that, you can calculate it. But here, the sound wave is traveling double the distance, right? And so you use the formula 2d upon t instead of speed is equals to distance upon time, because they're traveling double the distance. Right, now you have to draw a graph for compressions and rarefractions. Over here, you have these particles that are at their original position. When these particles move in this direction, and in this direction, this region becomes a rarefaction. And this pink particle is the center of rarefaction. And when the particles move in this direction and this direction, this becomes a compression with this red particle as the center of compression. And so we want to plot a graph for it. How would it look like? So I say that, for example, this particle was displaced. This particle is displaced at 0. It doesn't displace. But then my next particle over time is displacing, say, 5 centimeters. And then my next particle is displacing just 1 centimeter. I can put it here. And then when it's displacing in the opposite direction, I can take my displacement values in negative. And if that's how my graph forms, these minimum and maximum values are going to be the same, but the main idea was that your graph is going to form in this manner for your displacement time graph. Displacement time graph. So this is how it's going to look like. This is your compression, and it's plotted at 0 because there is no displacement. This is the center of compression. This one was displaced maximum towards the left, so we plotted it at the negative most value, the bottommost value. This one was displaced maximum towards the right, so we gave it the height. And so this is known as the amplitude, which is the maximum displacement of a particle from its rest position. To understand a cathode ray oscilloscope, here I have a receptor A and a receptor B, and both are going to receive the sound wave at different times and give different readings. So over here, I have 1, 2, 3, 4, 5, 6. If I start from this point, I should end at this point, and in between, I have 6 divisions. Okay, when I have 6 divisions, and I know that receptors A and B are placed at a distance of 16 meters, there's a distance of 16 meters between both receptors. So I have the distance of 16. I have the time as 6 into 4 into 10 raised to the power negative 3 because I've set it at 4 meters, at 4 milliseconds. So since it's set at 4 milliseconds, to bring that milli to seconds, I'm going to multiply by 10 raised to the power negative 3. And since there's 6 divisions, I'm going to multiply that 6 with my 4 milliseconds. And for that, to find the speed, this is what I do. I divide the distance, 16, with 24 into 10 raised to the power negative 3, and I get 666 meters per second as the speed of sound. So this is once again the indirect method. This is how you can check if sound echoes. You can use a cardboard tube. Sound wave is going to travel here at the exact same angle. It's going to reflect, and this soft wood in between can be taken as your normal in an angle. And so you should hear the sound over here, which will show you that sound echoes. Then, how can you use echo in your practical daily lives? So ships use echo. What do? They transmit a sound wave that is reflected back to the ship, and so they can find out the distance from the seabed and the ship. So the distance is 180 meters. How did they calculate that? They knew the speed of the sound of the sound wave they sent. We all know it's 1500 meters per second in water. And so they sent it down, and then they calculated a time in which the sound wave echoed, and then using the formula, they calculated the distance as 180 meters. What are the 3 characteristics of sound? Pitch, loudness, and quality. Pitch is related to frequency, loudness is related to amplitude, and quality is just also known as timbre. And it depends on how your wave forms, whether it's noise or music. So noise would have a low quality or timbre, and music would have a high quality or timbre. Okay, so now we need to discuss a very important relationship in using the formula of speed. Up till now, we just discussed speed is equals to distance upon time. But now let's discuss another formula. Speed is equals to F lambda. And a very important relationship that can come in your examinations is between them. So we need to see the relationship between the speed and frequency if we keep the wavelength constant. So if my speed increases, what happens to my frequency? How can I check that? So I'll take an example. If my speed is 20, my frequency is 2 So obviously my wavelength has to be 10 for that to be equal to it. But if I increase my speed to 30 and I keep my wavelength constant because I need to check the relationship between speed and frequency, what happens to the frequency? It has to be 3 to make this equation correct. And so as the speed increased from 20 to 30, the frequency also increased from 2 to 3, which means that speed and frequency have a relationship of direct proportion. But if now I want to check the relationship between frequency and wavelength, so I'll keep the speed constant. So if my speed was 20, my frequency was 2, my wavelength was 10, and I increased the frequency. What happens to the wavelength? 20. My frequency was increased to 4. For the equation to be correct, my wavelength has to be 5, right? Because 4 times 5 is 20. And so my wavelength decreased, which means that frequency is inversely proportional to my wavelength. And now, if you want to check the relationship between speed and wavelength, so I increase the speed from 20 to 30. And if that's constant, it has to be 15 for the equation to be correct. And so when my speed increased, my wavelength also increased. And that is the relationship between all the three values in my formula. Speed is equals to frequency into wavelength, or V is equals to F lambda. Coming back to the characteristics of sound. So the first characteristic is loudness, which depends on the amplitude. If you have a greater amplitude, then you have a louder sound. And if you have a lesser amplitude, a lower amplitude, you have a softer sound. And how do you decide the amplitude? We discussed that the amplitude is the maximum displacement of a particle from its rest position. So this is the maximum displacement. And here, this is the maximum displacement. So it's very clear that the amplitude of this wave is larger, so the sound is louder. Pitch. Pitch is related to frequency. If I have a lower pitch, it means that I have a lower frequency. There are less waves per second. Frequency is the number of waves generated in 1 second. So over here in 1 second, how many waves are being produced? Generated 1, 2, and 3, and a quarter. Over here, what's the frequency? In 1 second, we have 1, 2, 3, 4, 5, 6, and a quarter wave. So since this has the higher pitch and the higher frequency, this tells us the relationship between frequency and pitch. When your frequency increases, your pitch also increases. So a sound wave with higher frequency will generate a sound with higher pitch. Then the quality or timbre of a sound. Quality and timbre are the same thing. Why is this music and why is this noise? If I have a wave generated smoothly, there is even displacement of particles. So that is a sound wave with good quality, or that's music. But if I have a wave that has irregular displacement, so my graph has irregular points like that, instead of over here when I had proper points so that I could form a smooth curve, then this has a low quality or a low timbre, and it becomes a noise or a nuisance to the ears.